Let's talk about regular expressions. A regular expression is a specific kind of text pattern that you can use with many modern applications and programming languages. Regular expressions are created using the regular expression language. And like any language, regular expressions have a specific syntax and instructions. In fact, regular expression language is not a full programming language. And regular expressions are designed to solve a very specific problem: search, match, extract, replace. We can use them to verify whether input fits into the text pattern. For instance, you need to verify that specified address is formatted correctly. We can use them to find text that matches pattern within a large body of text. We can use them to replace text matching the pattern with other text, or even rearrange bits of the matched text. In fact, regex can simplify our text preprocessing tasks. Regular expressions are also widely used in practice. Think of major text editors, spreadsheets, Google Analytics, and there are several analytical and technology platforms support them, including SQL, Python, R, Tableau, and others. The idea of regex was originated in the field of neuroscience. In 1943, neurophysiologists McCulloch and Pitts developed models describing how the human nervous system works and how a machine could be built like a brain. In 1956, a mathematician Kleene described these models with an algebra he called regular sets, and the notation was regular expression. In 1965, regular expressions are for the first time mentioned in the context of computers. Ken Thompson, one of the key developers of Unix, implemented regular expressions inside the text editor he called ED, or ED. That's the entry point of regex into the computing world. At text editor, and you're probably familiar with the grep command, it has the functionality to search based on regular expression. And in 1973, Unix released a standalone program called grep. One more milestone: during 1970, Alfred Aho has extended grep with a whole bunch of new functionalities, modify syntax, and name it as egrep, extended grep. Of course, to use regular expression, we need to define a regular language. A regular language is a language that can be expressed with a regular expression, or a deterministic or non-deterministic finite automata or state machine. Think of language as a set of strings, which are made up of characters from a specific alphabet, or even set of symbols. Regular languages are a subset of the set of all strings. Regular languages are used in parsing and designing programming languages. Now, regular expressions and finite state automata are very similar. And since finite state automata can be represented as graphs, let's look at the morphology rules as an illustration and how we can build morphology analyzer using language rules. Morphemes in many languages are typically arranged in a certain order. Working is the correct statement, but using ing before work would be incorrect, so the order must be maintained. Some morphemes also belong to a closed class. For instance, plural agreement in English is normally expressed with s at the end of the word, as well as the third person singular present in our tense agreement. So, can we build a morphological analyzer that can parse and produce these three rules: inflection S, inflection ed, and inflection ing for two words, walk and talk? Here we have a directed graph for creating morphology rules. We have label transitions, states, and one-directional arrows. We also have a start state And we also define a set of final state marked as a blue nodes. Our rule here can create the word walk, then a third person singular walks. Notice the blue node. We can create past tense, walked, and also gerundive, walking. We can add an additional label, T, so we can form the following words with talk, talks, talked, and talking. So all the morphology rules are preserved. Can we represent these morphology rules through regular expressions? And here's an illustration. Pipe here means a Boolean OR condition. Question mark will show that the morphemes are optional. Before we learn syntax, here are a couple of scenarios where other tools might be actually better than regex. Regular expressions are not suited to parse HTML just because HTML is not a regular language. You'll be better off using specifically built HTML parsers. We would also avoid parsing URL path and query parameters with regex, because most standard libraries have mature tools to pull URL apart. Email address is another example of complicated data that isn't well suited for regex. Here's an example of regex to parse most but not all valid email addresses. A regular expression is a pattern of text that consists of ordinary characters, literals, for example, letters A through Z, or numbers 0 through 9. And it consists of special characters known as metacharacters. The literals here are white space and a letter A. And the metacharacters in this example is \W that matches any alphanumeric characters and an asterisk that will allow any number of repetitions of the previous character. So the pattern we created here will match any word of any length starting with A. To learn and practice regular expression syntax, we'll be using first the online platform regexR, where you can just paste your text and experiment with regular expressions. Let's start with literals. They are the simplest form of pattern matching in regular expressions. Let's take example, a sentence. The quick brown fox jumps over the lazy dog. If we build a regular expression, FOX, and search our phrase, we will find one match. And by default, notice the regular expressions are case sensitive. But instead of explicitly typing each character, we could define them as a character classes. Here we can match only lower cases or upper cases, only digits, by building our character classes sets. We have 12 characters that have a special function when used in regular expressions. If we need to use them as a literal character in a sentence, they must be escaped with a backslash. Let's revise our sentence and add parentheses around the word fox. Let's search for word fox with parentheses first. You notice the results do not include parentheses. This is because parentheses is a meta character and it needs to be escaped with a backslash. How about question mark? If you need to find the end of the sentence with a question mark, by placing question mark only, we will not succeed. But by escaping character question mark, we can actually identify the end of the sentence. Recall also from the previous slide that we defined our character classes, and we use square brackets and hyphen. Remember 0 through 9? So square brackets and hyphen here used as a meta characters. We could actually combine ranges and create an alphanumeric class even from 0 to 9, A through Z, upper and lower characters. Or we can even negate class. For instance, if we place caret symbol in front of our character set inside the square brackets, this expression will match anything that is not a digit, as in this example. It is worth to learn several shortcuts for character classes. Note that without repetition, our match will always return one single character. There's a number of predefined character classes that can be used. Dot, by itself, matches any character except new line. \D will match any decimal digit. It is an equivalent to the class 0 through 9. \D will match any non-digit character. It will be equivalent to the class of negation. \S matches any white space, including tabulation, new line that can be marked as \N, \R, uppercase S matches any non-white character. \W lowercase matches any alphanumeric character. This is a great shortcut to represent alphanumeric set. And finally, we have \upper character W will match any non-alphanumeric character. So this will be negation of alphanumeric set. So far, we have learned how to define a single character. Now we need to define how a character set can be repeated. We have three basic quantifiers: the question mark, plus sign, and the asterisk. Question mark can be used to match the word car and its plural form cars. You notice we have a question mark after S. Alright, how about this problem? Suppose we have three variations for phone number input, with a hyphen, with a space, with no spaces. Let's use a shortcut for digit, \lowercase d, with quantifier plus, which means one or more times. Of course, we'll need also to include optional space or hyphen. How we're going to do that? So we can create a character set with square brackets, with hyphen, and \s representing white space, and add question mark to make it optional. So we'll repeat it one more time, and finally add d plus at the end to include the entire phone digit number. If we know that we have only 3 repetitions of digits, for instance, the first 3 digits in the phone number, we can use curly brackets and we can define exact number 3. Or we can also establish range between n and m times if needed. Consider now the following task: extracting text between quotation marks. So we can match any character between quotes, right, and repeat it one or more times. Perfect. However, if we use representation on the left, it will create a greedy quantifier. What does it mean? In fact, if you try out on your own, you'll see that it'll try to match as much as possible and to have the biggest match result possible. So it will pull everything between those two words that we're looking for, in this case, hello and hola. The solution here is to use reluctant quantifier that would try to have the smallest match possible. To do that, we simply add question mark after plus sign, and it will behave like the exact opposite of the greedy quantifier. It will try to match the smallest match possible. In this case, it will pull exactly what we need. Until this point, we built our regular expressions within a text. But sometimes we may also need to match text at the beginning of a line or at the end. So we have a boundary matchers. The boundary matchers are a number of identifiers that will correspond to a particular position inside of our input. Let's match the word hello at the beginning of the sentence. We will use a caret symbol. You probably remember that we use caret symbol before to mark negation. That's correct. But it was placed inside the character class set. Remember, inside square brackets. Here, without square brackets, it identifies the beginning of the sentence. The end of the line is identified by $. To match a word boundary, we can use \lowercase b. And let's look at the example of extracting the word hello that is located at the beginning of the line. Let's look at the example here that identify and extract the word hello and skip the other version containing hello as a part of the word. Alright, now you're going to ask me what happens if word boundaries are configured for a different language. Good question. The answer is these boundary matchers will behave differently in different contexts and it will depend on the configured locale in your machine. Alright, this is a very brief introduction to regular expressions. For more practice in regex syntax, consider interactive exercises using, for instance, regex 1.